Join. यहाँ पे कहाँ टीम्स में ज्वाइन रेडी ये शेयर कर सके We'll start. Okay, dear learners, welcome to this live session for this course Power Plant System Engineering under NPTEL platform. So by now we must have running this course almost about a month. So we are also in touch with you in various forum, mainly through discussion. So during this discussion forum, we have come across several questions, and of course we have given some of the answers during the discussion phase itself. However, I feel that some of the questions or some of the concepts are still not clear. So I thought to revise those concepts in this live session. So one question was raised in lecture number 2, week number 1, when we are discussing about the numerical problem 2 about exergy. So questions was, can you please share the table in the solutions of superheated steam? Second one is why you use the superheated steam, not any other table. Anyway, this part I'll explain a bit. As far as the concept of this part of these questions, I have explained in the module number 1, where I have discussed about properties of pure substances. But again, I'll try to re-emphasize those facts in this live session as well. So in the subsequent slides. The other important point while talking about exergy, we come across the term dead state. Dead state is a standard term. It is actually predefined state because that is the state the system cannot go below that conditions, and that is mainly decided with the parameters pressure and temperatures. So unless and until it is given in the questions, we blindly assume this is to be 100 kilopascal and 300 Kelvin. Anyway, this number has to be given when you solve the problems. So if nothing is given, then you can straight away use these numbers as a dead state parameter by mentioning that this terms has been assumed for the dead state. So in fact, while calculating exergy potential, dead state numbers is required. Again, in this exergy analysis, we use the term T0 into S minus S0. S minus S0 stands as the entropy difference. S stands for entropy at a given state, and S0 subscript 0 stands as entropy at the dead state. So difference in the entropy multiplied by the temperature of the dead state will give you the exergy calculation, specific exergy. But however, when you use this expression, it has to be ensured always that and temperature has to be defined in the Kelvin scale only. So irrespective of dead state conditions, if it is given, you have to convert it for evaluation of exergy. So I believe that learners is supposed to ask whether you use Kelvin or temperature scales. So by default, whatever may be the question, whether it is the data is given in degree centigrades, you must convert it to the Kelvin. So whatever form, it has to be converted to Kelvin for calculation of exergy. So I hope I have answered this question. Then third questions is about again the numerical problems of week 2, where please share the thermodynamic tables. Anyway, this part I will explain. Another point that people try to explain the expansion process where it starts from 3 to 3 dash. Actually, if you refer this particular figure, like this particular diagram refers to the fact that we are highlighting the fact that steam enters this turbine at state 1, it expands in the first turbine, then again it is further reheated to state 3, then again expands to state 4s. So basically speaking, we start with a superheated steam which is 480 degrees centigrades. When it expands isentropically, so expansion process is decided by the process 1 to 2s. Now if this expansion is non-isentropic, so that is what the entropy must increase. So the point 2s shifts to 2. Similarly, during the reheating process, that means after at point 2 again it is reheated to state 3 at same pressure, and then at this temperature it further expands in the second stage turbine, that is WT2. So in the second stage turbine, if the process is non-isentropic, this entropy increases. So 4s stands to stage to 4. Now such a process 1, 2 or 3, 4, they are non-isentropic process. So why I am saying that when in the given problem, if the isentropic efficiency of the turbine is given, then it is assumed to be that process is then you have to use this data isentropic efficiency of the turbine to evaluate the state points 2, 3. In this case, it is 2 and 4. So that is what we say. The line shifts from 3 to 3 dash or 4 to 4 dash. So actually, it is actually it is a non-isentropic case. We have to please explain the name of the entropy and enthalpy or any name like HS. I will explain this point when I go to the subsequent slides. So more or less we have given the answers for each of the bit questions in the discussion forum itself. Of course, I have clarified those things in this live session. And during the discussion forum, the most important part people are asking about the concept of steam tables, why we are going to use it. So for that reasons, I suggest you to revisit any book with topic, any thermodynamic fundamental books with a topic called as properties of pure substance. And here there we come across the term called as pressure temperature diagram, normally referred as the phase diagram. So essentially when you say pure substance or the substance exists in three phases, solid, liquid and vapor. And in the pressure temperature diagram, there are three distinct lines that that distinguishes between between the intersection of any two phase. For example, solid and vapor, they are separated by a line called as sublimation line. Solid and liquid, they are separated by a line called as melting line. Liquid and vapor, they are separated by a line called as vaporization line. So there are some solids, there are some substances that expand during a freezings. So that also have another characteristics is shown as a dotted line. But whatever may be the case, we are now here while talking about steam table. We are essentially looking at the what happens between liquid and vapor phase. We are nowhere we are looking at the solid phase, whatever between liquid and vapor phase. Now when we say liquid and vapor phase, there are the 2 points are separated by a point what is called as critical point. And when solid, liquid and vapor coexist at a particular pressure and temperature, that is called as a triple point. Now for steam tables, triple point has no role. So we are now will be looking at what changes that happens between liquid and vapor state. So let us talk about a pure substance which is water. So initially it is in liquid state and we are trying to represent this state, thermodynamic states in the temperature volume diagram. So in a temperature volume diagram, when it is at state 1, that means that substance or water exists at 20 degrees centigrade with certain volume. Now that particular point is normally thermodynamic term we refer as a complete liquid region or compressed liquid region. So if you keep on heating this liquid, so that means when the temperature reaches to 100 degrees centigrade, there is a change in the temperature. So this change is called as a sensible heating. So during the sensible phase of heating, the temperature goes and at this point too, the liquid starts vaporizing. So all of a sudden, all the liquids do not vaporize. It takes some finite time. So slowly vaporization process starts. So as the vaporization process moves, the point 2 moves towards the point 4. So this particular process, the vaporization process, happens at constant temperatures, and but there is this since it is a constant temperature and there is a change of heat. So this particular change we call as a latent heat. That means the change of phase for a for the substance. So at point 4 complete, so initially which was state 2, which is the complete liquid state, and we call this as a saturated liquid, and at point 4 complete liquid becomes saturated vapor. So liquid becomes vapor, and any intermediate state between 2 and 4 it is state 3. So it's a mixed region, where you say liquid vapor region. And come at point 4, if you add further heat, already vapor you have reached, so again temperature goes up. So these things goes up, and again it is in temperature goes up at same pressure. So we call this as a further sensible heating. So complete process happens at one pressure. Now, if you that is one atmospheric pressure. In this case, low atmospheric. Similar curves can be drawn for other pressures as well. Then if you do that, then we can get a curve like this. One is the temperature volume diagram. We can get a curve like this, and we call this as a dome. And in this dome, we define a point called as critical point, which is the only one point. Like below this point, there are two distinct points, which is the saturated liquid and saturated vapor. And these 2 points merge to a single point at one particular temperature and of course at one particular pressure. And that is called as a critical point. So at this critical point, both the solid line, the saturated liquid line and saturated vapor line meet, and that is the critical point of the substance. Similar curves, this is when you say pressure volume diagrams, the temperature lines are opposite in nature. And in this side, we are increasing the pressure. If you are going up, we are increasing the pressure. And here, if you are going up, we are increasing the temperatures. So this is all about the three distinct regions. This is complete liquid, this is liquid vapor, and this is superheated region. So whenever you use the steam table, that means it gives you the data for how to obtain the data in the compressed liquid regions and saturated liquid vapor regions and superheated region. Another important point is like that, like when you look at compressed liquid region, we need two parameters to define the state. But when you are in the liquid vapor regions, either pressure or temperature is any one parameter is sufficient to define the states. So that is what we have a curve called as saturated pressure and saturated temperature change at a given. So let's say if you are talking about this line, it is at a constant pressure. So we know that that is the saturation pressure, and correspondingly we can come in this graph and find the corresponding saturated temperatures. So this is all about the concept of various phases or states of the system, mainly liquid vapor region. Now we are going to give more details like how to quantify the data or number. So for example, at this state we have a this at pressure, and similarly for saturated vapor, Vg is the specific volume of saturated vapor. And when you say any intermediate point, and Vg and Vf will give you the average value of saturated liquid vapor mixture, which is somewhere in this intermediate point, as you can see in this figure. So a B point refers to a region where we have saturated liquid and vapor region. Now in these things, this specific volume at this state is always greater than the specific volume of the desaturated liquid, but less than the specific volume of saturated vapor state. So that way one can quantify mathematically by defining a fraction, a term called as dryness fraction X. So X can be calculated. So once you know X, all other parameters, average value of internal energy, average value of enthalpy can be found out by knowing the numbers, corresponding numbers at there in the saturation curve. So that is the theme of the steam table. So basically there are three distinct regions. One is compressed liquid region, which is in this dome. So for that we require two parameters, and if it is a liquid, it's incompressible. Since liquid is an incompressible fluid, maybe one pressure or temperature is sufficient to define that data, because all the numbers fall on this saturated liquid line. Now, when we go to the superheated regions, so essentially we are looking at a point, any point on this pressure curve, which is much above this saturated vapor curve. So for that region situation also we require two data, 2 points or two thermodynamic states to define the states. So let us see how we are evolving all these things. So by combining all these things, we define the steam table concept. One is for saturated water. This steam table is defined for water. When the water is at, we call this as a saturated water temperature table. We say saturated water pressure table, because when you are when you when you are talking about saturated liquid line and saturated vapor line, one parameter is sufficient to define the states. So it varies temperature. That means if you are comfortable or data is given in terms of temperature, we refer saturated temperature table. If the data is given in terms of pressure, we refer saturated pressure table. So once you have saturated pressure table or temperature table, corresponding number, either pressure or temperature, is defined here. So once you know this, if you go along this line, horizontal line, so we have specific volume data, we have internal energy data, we have enthalpy data and entropy data. All these points refers to saturated liquid and vapor line. Another term that we use, that what is HFG. So HFG is a term that is nothing but the difference between the enthalpy values at saturated vapor state and saturated liquid state. For example, if I say HFG, which means Hg minus HL. So for example, 2336.1 we got by taking and difference between Hg, that is 2625.3 minus 289.23. So that way the data is as are presented here. So this is about the what data we require in the saturated dome, liquid vapor, saturated vapor line and saturated liquid line, and in between this saturated liquid vapor region. But when you go for the superheated vapor region, we require two two parameters, both either two thermodynamic parameters. So tables are plotted for various pressure values, temperatures are given. For example, if you want to look for the superheated water vapor data at 10 bar, 320 degrees centigrade, then you have to go along this line. If you want to look at the pressure data at 15 bar and 360 degrees centigrade, then you have to go along this line. And this stream table is available free in the everywhere in various platforms. But for the learners, and we are using this book Moran and Shapiro, Principles of Thermodynamics, and that is table A2, A3 and A5 for this particular course. Whatever problems are being solved, the data for the tables are given here. But however, another point, important point for this steam table corresponding to that we come across is the Mollier diagrams. It is nothing but the enthalpy and entropy diagrams at various pressures and temperatures. So for the learners, if you are going for exam point of view, you need not have to worry, because all the data will be supplied in the problem itself. But however, for learning purposes, you can refer the books, what is steam table, how you extract the data at a given parameters. So all these things for learning purpose you can explore by yourself. So this is one simple problem which was solved based on the steam table things. So a rigid tank contains 8 kg of water at 90 degrees centigrade, in which 6 kg of water is in liquid form, and since it is 8 kg, so remaining form is vapor will be 2 kg. So basically the tank has 90 degrees centigrade with 8 kg of mass, out of which mass of water form you have 6 kg and vapor form you have 2 kg. So from this we can find a term what is called as a dryness fraction. So it is essentially in the steam table, it is the liquid vapor region. So we can find the dryness fractions. Since we have 90 degrees centigrade data is given, so you refer saturated temperature table at 90 degrees centigrade, corresponding saturated pressure we can find out 70.14 kilopascal. Now again at that temperatures, if you take the specific volumes values, Vf and Vg, So VF and VG values at 90 degrees centigrade come somewhere here. So from this we can get the data VF and VG, and since we have already known mass, so specific volumes can be calculated. So total volume can be estimated. So this particular problem demonstrates how to use the stream table, and here in this case we have referred saturated temperature table or pressure table. Another problem which is of similar nature, but the problem refers in the superheated region. For the superheated regions, we have parameters, we require two parameters, pressure and temperature to define a state. But the given problem that says that we require uh, data, we want to find the temperature of water at a pressure 0.5 megapascal and enthalpy 2980 kilojoule per kg. So basically, it is indirectly meaning that temperature is not given, but you have to find the temperature. But in place of that, what data is given is the enthalpy. So you have to do some kind of interpolations in which what you have to start with, you start looking this data. What is the saturated value of enthalpy at enthalpy in the saturated vapor line? So that for that we can refer saturated pressure table at 0.5 megapascal. We arrive at the Hg as 2748.7 kilojoule per kg. But our actual value is 2890. So obviously it is in the superheated region. So for then what we have to do, we have to take zero point 0.5 megapascal or 5 bar pressure line and try to find out locations where this enthalpy value lies. So if you can see somewhere enthalpy values 2890 falls somewhere between 200 to 240 degrees centigrades. So that means we have to do some kind of linear interpolation to find these values. So typically, if you do these linear interpolations, so actual number would be 28. At that enthalpy would be 218 degrees centigrade. So this is how it gives you the demonstration how to explore the steam table. So this is all about from my side what I try to say. So let us see these questions one by one. One question is used that how regeneration is used, how will be helpful for increasing the thermal efficiency. I mean, why to make the steam again to extract so far to heat water or open water feed water. See, the regeneration concept is used mainly for improving the efficiency because thermodynamic viewpoint says that in a single go, don't expand all the steam because there is always a chances of loss. So rather you use this expansion in sequential manner. So that process called as regenerations. So through regenerations, we are actually tapping some amount of fluid for to use it in various purposes. For example, if you tap the some amount of um, fluid in the regenerator, what happens is that it improves the cyclic efficiency because because uh, additionally we do not need any extra heat or power to run some of the components or device. So that is the basic things what is normally done in an open what feed water heater. So I hope I have answered this query. Any other questions, please raise. One learner is Mr. Atul Misra is asking, I am currently pursuing PGDC in power plant system engineering. Please guide me for interview point of view and also how to brief first how this course will help about the certificates of importance for this NPTEL. So it is highly appreciated that you are pursuing this course on power plant engineering. So basically, this particular course is a blending between two conventional power generation systems. One is classical way in which power is generated through steam power system, and since and for which the main fuel is your coal, but and it is comes under the category of fossil fuel. But nowadays the fossil fuels are depleting day by day. So because of this depletion, what happens is that we require some kind of new innovative ways of uh, um, generating power or at least augmenting the conventional based power systems. So the harnessing power is done from various resources such as solar energy, wind energy, then we have geothermal energy, then we have fuel cells, batteries. All these things are, we can say, energy storage systems. So this comes under, and moreover, we have hydropower systems. All are treated as a renewable form of energy. So this particular course will help. What is the conventional way we can extract energy or power uh, from the conventional resources, and how to augment it through the new technology based renewable power generation systems. So if you look at the complete syllabus, 50% of these lectures are devoted for conventional based power generation systems, and rest 50% are devoted for renewable based power generation systems. So that is what, and if you take the exam, you will get the certificates which will be helpful in for credit transfer wherever you have registered. So I think this is what I want to uh, uh, advise for your queries or question. So if there are any other questions, please raise in the chat box. We have hardly 10 minutes left, so please be in a hurry. Why do you need to maintain vacuum pressure in the condenser? Thermodynamically, it will increase efficiency, but practically, how is it helpful? It's a very good question, because if you don't maintain vacuum, we essentially, if you look at the condenser location, the steam expands in the turbine and enters into the condenser. So for the for a continuous flow of steam in a um, in a in a steady rate, we expect a pressure differential has to be maintained between the condenser between the boiler pressure and or turbine pressure and condenser pressure. And normally what happens if you maintain it at atmospheric pressure, we are actually expanding the steam up to the atmospheric pressure, and because the condenser is maintained at that pressure only. So normally to harness complete energy from the steam or to improve the exergy potential of the steam, we expect that we expect that we expect that condenser should operate below atmospheric, so that steam what when it exists to the condenser, it has a very less amount of energy available, or in other words we are saying we are we are improving the exergetic efficiency of the systems. So that is the reason we say it improves the efficiency thermodynamically, and the condenser pressure is always maintained lower than atmospheric. So I hope I have answered this question. Andrew Smith, very good evening. If you have any queries, please raise your views. It's nice to see you in this NPTEL platform. Probably you are abroad, and I hope you are enjoying this course. And if you have any queries, please raise your views. We have 5 minutes more. Next question is why is it not possible to increase the efficiency of the power plant beyond 40%? See, ideally speaking, power plant efficiency doesn't go beyond 40%. The main issue is that if you look at the heat balance, first of all, uh, you recall the Carnot cycle, where the second law efficiency puts a limitations of the Carnot cycle. That means we have source temperature and sink temperatures. In that source and sink temperature limits, the Carnot cycle gives the maximum possible efficiency. Or in other words, it says that complete conversion from heat to work is not possible. So there is the efficiency upper limit, that is Carnot cycle. Apart from that, when you say power plant, there are various components involved, like boiler, turbine, and within the boiler, there are superheater, there are reheater, there are economizers, there are so many components. Again, we have a condenser, we have pumps, we have turbines. They have their own efficiency. And while doing so, and on top of that, the atmosphere or exergy, if you look at atmosphere, which is a considered a dead state, that is also there. So each component has their own efficiency. So basically speaking, there are some unavoidable losses which is involved. Component losses are always there. Component losses in terms of pressure and temperatures at each location is always there. And there is always we have to reject heat to the surrounding as well. So consider, and of course there is upper limit of temperature, that is Carnot cycle efficiency is imposed. So considering this, it has been estimated that steam power cycle doesn't have efficiency more than 40%. That is true. But however, there are some partial improvement in efficiency that we can do by using the concept like reheating, regeneration. So all these things are superheating. So all these things are done within the boiler itself to improve this efficiency marginally. But that again, it's a that number is a good number because when you are looking at a large scale power plants, 2% efficiency saves a lot. for the complete system. I hope I have answered this your queries. Thank you. So, porous materials are used in the preheater. See, these porous materials has nothing to do. Materials as I have not covered any kind of material is expect in this preheater. Rather, I have just talked about the kind of design that is normally done in the preheater. Preheater is nothing but an heat exchange between the air and the from the steam. But however, in our case, we don't use the concept of materials. But normally, there are some materials, porous materials that are as a uh, kind of a heat storing or phase change material devices that can be looked at in the preheaters. But however, that is not the purview of this course. So we are almost in the closing session. So another 2-3 minutes we'll try to wind up. And this is the final call to import raise your queries. So please be in hurry. Of course, I regret that due to technical issues, we are late by about 12 to 15 minutes. So that is again beyond our control. So I regret for the inconvenience. How is next question? How is high pressure is achieved 220 bar practically? To achieve high pressure, uh, uh, we have to do this rise in the pressure in the stages. Uh, 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 Normally, the uh, the as I mentioned in the steam generator unit, there are uh, there are different components, and we have you employed draft fans, induced draft fans, forced draft fans. So these draft fans induce necessary pressure differences. And again, during this expansion, during in the boiler itself, the different components work at different pressures. So, so if you look at global point of view, so entire system works in stages, and we that makes us possible that we can go up to that pressure. The pressure is raised by the pump. That is one thing, feed water pumps. And also the pressure is also created by forcing the air into the systems and taking away the combustion products using the fans. So pumps are the only means that raises the pressure. Means in when you talk about pressure range in the up to uh, 220 bar. And thermodynamically, boiler doesn't give any kind of, because entire things happens at boil in the boiler system happens at constant pressure only. Okay. Supercritical. So you are talking about the supercritical parameter. So in this supercritical plant, which is not the purview of the case in this course, here we do not go through liquid vapor lines. That means we go beyond critical point. So beyond critical point, there are uh, of course supercritical plants do exist. So that pressure driven, basically we are going liquid to vapor significantly by to we are going from liquid to vapor directly without entering into liquid vapor regions. So for that supercritical power plants, normally with conventional steam-based system, it is not possible. But if it can be integrated with nuclear power systems, so there it is possible. But with conventional mechanical devices, going for 220 bar pressure may not be a feasible task. Of course, there are some devices, I am not sure about how that supercritical power plant or what components that raises the pressure to 220 bar, but there the technology do exist, what we see in the supercritical power plants. Obviously, nuclear power plant is better than the conventional power plant because that is treated as a fossil fuel based, I mean carbon free emissions. But however, main issue of nuclear power plant is the how to discard the nuclear materials, like the so that is, but that still in our country that technology still has not come in place. But of course, it is better than conventional power plant thermodynamically. Maybe the nuclear power plant is the next generation, and of course, it comes under the renewable energy forum or platform. So obviously, it is better than the conventional steam power systems. Okay, thank you for your kind attention. Thank you for your questionnaires. I hope you will be enjoying this course. So again, your question is that there is a scope of porous materials in a power plant. I think thermodynamically, porous material has no role but usage of porous materials in the power plant has a different, of course, it's a usage of material. If those porous materials can be considered as a phase change materials, then it may be useful for the power plant technology. If you are thinking these porous materials as your research purposes, then think about those porous materials which can be considered as a phase change materials, in which the heat exchange can be possible. That is one point, like wax. Wax can be considered as a liquid or solid. So when you add heat, it becomes liquid or it starts melting. But when take out heat, it becomes again solidifies. So that way becomes a heat exchange mechanism processes, and then it will be useful for power plant concepts. So in this line, you can think about for your future work or need or discussions or research. Okay. Uh, so let us close this session for today. We'll have again another live sessions. So uh, keep your discussions in the discussion forum itself. So we'll try to answer your queries, and in the next live sessions, please come forward with variety of questions so that we can discuss. With this, I sincerely thank to all of you to have the patience for our late starting of our course due to technical glitch. Once again, I thank you for your kind attention.